All right, so our Indie Lab presentation, it's on, or just have to do Preston.
I don't know. I hope not. Oh, PowerPoint. Boo.
All right, so the purpose was to find the spring constant of a trampoline, and then we did this by, what we were gonna do, just look at the individual springs in it, and then try to like work with those to find the spring constant of the whole thing, but it was kind of difficult. And then we also wanted to see the differences in the spring compression and the masses in the center and like off center. So our hypothesis was pretty much it would be the same if the mass is in the center, because it's like the same force would be exerted equally around the trampoline, and then closest, like the springs closest to the mass, like which yeah,
Yeah,
the
so they'll,
special one.
yeah.
Like the ones with the smallest radius. So you just use Hooke's law pretty much. And then there were a lot of springs in a trampoline, and we didn't really account for that, so we didn't look at each one individually. We just like kind of picked basically a pentagon. So we went like that and just picked 5 or like 6, and then that was like gave us a pretty good representation of them. So we didn't have to take all of the data points, so it's like a little less accurate, I guess, but I think it's still got the
Yeah, that's our error.
yeah. And then we averaged them, so it wasn't like a off position.
Okay, so we placed a mass that was 70.4 kilograms in the center of the trampoline, and then like Blake said, we measured how far the spring stretched. And then, like he said, we took 6 different springs from the different points around the trampolines, and we averaged that value. And then we found the spring constant was that number. And then, oh, well, we found that was before we averaged it, and then we averaged it, and we got 56.46 Newton meters. And then here's all of the extension. What?
All right, so this is like we just pretty much thought of the trampoline as like one big spring and found the spring constant of that. And then we did that by placing a 53 kilogram mass in the center and just measuring like how far down it goes. So like we found that was 0.13 meters, and then we used Hooke's law from there.
Were these masses human?
Yeah.
Ah.
Yeah, that was my friend, Hannah.
So, because it was just easier like that. And so we used.
I was just gonna say, like, because we were gonna
Ryan.
use a heavier object, and
Are you 7 for me, 7?
it would be hard to. The only mass or the only scale we had was like a human scale, so it was just easier.
And then, so we got the compression, and we had the force from the mass, and then we used that and just put in the Hooke's law, and got that the spring constant of the whole trampoline would be this value. And then that seemed like really big to us because it's like a big number, I guess, but it makes sense because like when you're jumping on a trampoline, how much more force, or like how much of the force comes back to you, like so you can jump up higher and higher. Yeah, and it kind of made sense when we thought about it like that. And the conclusions, I didn't put the data for like the springs compression and we put it like off center, but it was like our hypothesis was right. They had greater, the ones closer to the mass had a greater extension than the ones further away. And we also found from that you didn't go, like the last part, how it went down like 0.13 meters, it didn't go down as far when it was off center. So that might be because the springs some of the springs didn't have like the same effect on it, or I don't know, but that's what we found. So that's when I put the extension depends on position. I think that's good.
Thank you. We have time for a question or two.
Nice.
Yeah.
Do you know what happens on a double bounce? You know?
Oh, I looked at that. It's like, oh, double bounce. I'm not sure. I'm guessing it's because something. I'm not sure. I just know like on like when you keep bouncing up, you keep going higher because you put like more for like you have more potential energy every time, and then that turns into kinetic on the way back up, and it just keeps going up like that.
What's the source of that energy?
The spring.
I don't think so.
Uh,
You are getting more potential energy every time. So I guess what I'm asking is, how do you get more energy the second bounce than you had the first bounce?
You go. Well, isn't it because the potential energy at the top is greater than it was like the last bounce?
True, but that's what I'm trying to explain. Why is that the case? Why do you have more energy after than you do before? Is this a thing where we could get like a whole bunch of people and have them jump on trampolines and power New York City with it? Because if trampolines make energy, I want more trampolines. I already have 2, but I'll get more. Heck yeah, I have 2. Trampolines are awesome. But they're not free energy. So what's the source of that energy?
I'm not entirely sure.
And you, young lady?
I think Andy knows.
We want to ask him then?
Yeah, I'll ask Andy.
It's because of your muscles. Your muscles are expending the energy and adding it to the system.
Oh, that makes sense.
Chemical energy.
Work? You doing work? When do you do work?
When you jump back up.
Yeah. Cool. Any other questions?
Yeah, Thomas.
How do you think your bounce height would change if a trampoline had more or less springs?
I think you would go higher because there
If
are
you
more.
had more or less springs.
But if you had more, I think you would go higher
But why do you think that?
because there are more. It's like adding more force, pretty much. It's exerted back on you when you go back up.
Thanks again, guys.